Well, Chapter 3 was thermodynamics in its full glory, and it started with the first law of thermodynamics, which says that the only way to change the internal energy of a system is through the addition of heat or work, or the extraction of heat or work by the surroundings. So when we developed the ability to apply the first law of thermodynamics to a heat engine, we recognized that the Carnot cycle was the central focus for establishing the thermodynamic relationship between what you put into a heat engine and what you get out. So the efficiency of a heat engine is always defined by what you get divided by what you pay for. And what you pay for is generating the heat that goes in, and you do that by virtue of purchasing gasoline that's combusted in the cylinder, and you get a certain amount of work out, and then the rest of that heat is dumped to the environment through the exhaust system of the engine. But that efficiency, which turns out to be initially a very complicated representation of these various trajectories, turns out to be extremely simple when it's properly analyzed, and it results in this extremely simple relationship between the high temperature reservoir and the low temperature reservoir defining the efficiency of that heat engine. And so the news for heat engines, as we've said before, is that the efficiency for a heat engine is on the order of 15 to 20% for a gasoline engine, for example. But we used exactly the same principles to look at the heat pump and deduced the fact that the coefficient of performance for a heat pump is on the order of 5, which means just 1 unit of energy in produces 5 units of energy of heating or cooling. And when you think about this thermodynamically, you think that's a miracle. But it's based on a simple fact that nature looks at the world through the relationship to absolute zero, 0 Kelvin. And when you look outside and it's a day when it's just at the freezing point, you recognize that that's 273 Kelvin in temperature. But the temperature inside the room of your house is about 20 Kelvin higher than that, or 293 Kelvin. And that means that all you have to do is put in a very small amount of work to elevate the kinetic energy of the outside air at the freezing point to the kinetic energy of the inside air at a nice, comfortable room temperature. And that's why the coefficient of performance of a heat pump is so large. That is, it has huge leverage, leveraging the input of energy to the output of heating or cooling. Next, Chapter 4 brought on the concept of entropy. And entropy, as we saw, is a measure of the disorganization of a particular system. But it has a remarkable role to play in determining thermodynamic variables, because we can write the change in entropy delta S of the universe as a change in entropy of the system plus a change in entropy of the surroundings. And the simple statement that any spontaneous process increases the entropy of the universe has huge implications, not only for thermodynamics, but also, as we'll see, for electrochemistry. Now, what we want to do is we want to come up with a representation of the change in entropy in terms of the change in entropy for the system. That is, we want to exclude any relationship to the surroundings. So we use the first law of thermodynamics to say, well, we can calculate delta S, the change in entropy, as simply the ratio of the heat transfer divided by the temperature. That's a statement of the change in entropy. Well, the heat that moves from the surroundings to the system, or the system to the surroundings, under constant pressure is the change in enthalpy, delta H. Well, the first law of thermodynamics also says that because energy is conserved, whatever is gained by the surroundings is lost by the system. And that puts a negative sign here, but it produces a change in entropy for the system. So that means we've got the change in entropy for the system in terms of the change in enthalpy for the system, and we relate that back to the fact that any process that is spontaneous means that delta S for the universe is greater than 0. Now that's a very simple statement, and it's true, but it leads to the development of a new thermodynamic variable, namely Gibbs free energy. And that thermodynamic variable is Gibbs free energy is equal to the enthalpy minus the product of the temperature times the entropy. But we want to look at the change in Gibbs free energy, so we write delta G, and we confine ourselves to a condition of constant temperature. So this equality for T, a constant, means that delta G is equal to delta H minus T delta S. All right, well, because the change in entropy for the universe must be greater than 0 for a spontaneous process, it means that delta G for a spontaneous process must be less than 0 because of the sign inversion. And so the fundamental quantity that represents whether a process is spontaneous or not is delta G of the system. So in this case, delta G being less than 0 means that that process is spontaneous. So now we have our critical relationship that we can write in general that delta G, the change in Gibbs free energy, is equal to delta H minus T delta S. And the only thing that we have to be careful about is that that applies for constant temperature cases. But then we went on to develop the fact that delta G under any condition is equal to delta G plus RT log Q, where Q is the reaction quotient expressed as activities. And this is worked out as the central feature of Chapter 5. But that meant that we could analyze delta G at any point along a reaction. So if we started with pure products and we moved toward the equilibrium position, we are sliding downhill on the Gibbs free energy surface. If we started with pure reactants, again, we move downhill to a point where delta G is equal to 0. That's the equilibrium point. And so delta G tells us exactly how we can calculate that transition from either pure reactants to the equilibrium position or pure products back to the equilibrium position. Now there's one other important point that we made, and that is that we can calculate delta G under standard conditions but at any temperature if we're very careful to match the temperature we're doing that calculation with for the temperature that we want for the delta G calculation. And the reason for that is that delta H is independent of temperature and delta S is largely independent of temperature. So we can look up delta H under standard conditions, delta S under standard conditions in the thermodynamic table and carry that calculation out for any temperature.